Okay, folks, in this lesson we're going to look at some more examples of related rates problems and how they can be solved. And these are actually some of my favorite problems in mathematics because they're just kind of really fascinating to see how the different rates of change work with each other. So we've got this example of a hot air balloon that is rising straight up from a level field and is tracked by a rangefinder that is 500 feet away from the liftoff point. At the moment that the rangefinder's elevation angle is pi over 4, also known as 45 degrees, the angle is increasing at a rate of 0.14 radians per minute. And we want to know how fast the balloon is rising. All right, well, a picture is definitely going to help the cause here. So let's kind of set this up based on what we know. And if I'm drawing this picture, I have this sort of 500-yard distance, or 500-foot distance, that is in between where my rangefinder is and where this balloon is going straight up. So it's probably not much of a stretch to suggest that we have a right triangle at work here, 90-degree angle. Maybe you'll draw that a little bit more cleanly. There we go. Okay, so how high is the balloon off the ground at any point in time? Well, I'm going to call it h here. And the only other thing that I really have at my disposal is this angle of elevation, which is going to be right here in the corner where the rangefinder is, and I'm going to call that theta. And I call it theta because we call every single angle theta in this situation. So in order to come up with a good idea of relating theta and h and the 500, we start thinking about our right triangle trig, and we come up with SOHCAHTOA, and we're going to come up with the equation that the tangent of theta is going to be equal to h over 500. Okay. Good information to know there. We know that at this particular instant, when we sort of freeze the picture, we know that the rate of the angle's increase is 0.14 radians per second. So d theta over dt, our rate of change of the angle over time, is 0.14. But what we want to know is, we want to know what dh over d theta is. We want to, or dt rather, dh over dt. That's the thing that we really need to find out here in order to answer the problem, because it says how fast is the balloon rising. All right, so at this particular instant in time, when we've sort of frozen the picture, this angle is pi over 4. All right, well, that's going to be really helpful information to know, because I think that the tangent of pi over 4 is going to be 1. So at that instant, the height of the balloon is also 500 feet, which makes a lot of sense. But let's go ahead and see if we can get this dealt with here for a related rates equation. I want to solve this equation that I've come up with. I'm going to solve this for h. And when I do that, I'm going to get h is equal to 500 times the tangent of theta. And in order for me to get the differentials to pop up, I need to take the derivative of both sides. All right, so do this with respect to time. dh over dt is going to be 500 secant squared of theta d theta over dt. So at this point, at this moment in time, I can now plug in what I know for sure at this instant and find out what I don't. All right, well, what is the angle in question? Well, friends, the angle is right here. It's pi over 4. And what is d theta dt? Well, it's this 0.14. So I'm going to go ahead and do 500 times secant squared of pi over 4 times 0.14, and I have a feeling that that's going to give me the information that I need. All right, now this may be a little challenging on a TI calculator. What you'll want to do to get the secant squared is you'll want to take 1 over the cosine of pi over 4, and then whatever result that is, you'll want to square that off. Okay, so that's going to be the easiest thing for you to do in your calculator. Now, if you got a Inspire, or if you've got something like that, you can ask for it to do secants for you, which is just really quite nice if it's able to do that. So I'm gonna just take care of the secant of pi over 4 first in my calculator, because I think that makes the most sense. Then I'm going to square that off and then multiply that by 500 and then times 0.014 to get my answer here. Make sure I get everything in the right decimal point and everything. And what I'm coming up with is actually right on the button here, which is kind of nice. You might want to check my math on my end, but on your end. But I'm coming up with 140 as dH over dt, and that is obviously going to be in feet per minute, because our units of measure are feet and minutes here. All right, so that is one example of a related rates problem. Let's take a look at another couple ones here. All right, this one is a little bit more challenging as well, because we've got an airplane that is flying on a flight path that will take it directly over a radar tracking station. And the plane is flying at an altitude 6 miles when it is S miles from the station. And if S is decreasing at a rate of 400 miles per hour when S is 10 miles, what's the speed of the plane? All right, this is a little bit more difficult to kind of piece together, but we're going to do our best here. So we've got this radar tracking station, which is on the ground, and I'm going to put it right here at point R. And then I've also got this plane here, and this plane is going to be level, and it's going to fly right over the tracking station, and this plane is going to be 6 miles off the ground, a very consistent 6 miles off the ground. All right, now what is really kind of confusing here is this S. We don't quite know where to put it, so I'm going to help you out here. When S is 10 miles, well, we're going to talk about a direct 10 miles here is what we're going to do. Okay, so this is my S, and what I want to know is if S is decreasing at the rate of 400 miles per hour, what's the speed of the plane? Okay, well, this is starting to look like a right triangle again, but this time I think we're going to need a Pythagorean theorem set up. So I'm going to call this distance P here. And my given rate is ds over dt, because it's decreasing at a rate of 400 miles per hour, according to what I read in the question here. So I'm going to make that negative 400 in my problem. Now, another something that's kind of interesting here is this 6 mile measurement right here, how high the plane is off the ground here, 6 miles in the air. I'm going to tell you right now that has a rate of change of 0. There is going to be no change in the plane's altitude throughout the entire course of this problem. So we are not going to worry about that at all. This is a constant. All right, so friends, anytime that you have a constant when you start to construct your equation, that is not going to change no matter what. You can go ahead and put that into your equation, because when you take the derivative, it's going to drop out anyway. Okay, so our ds over dt, whoopsies, right tool here. Our ds over dt is negative 400. What we need to find actually is the speed of the plane. Well, what would the speed of the plane be? It would be dp over dt. So that's what we need to find here. So dp over dt. Alrighty. Well, let's kind of do two things here with this picture. I want to point out that we're kind of approaching our pictures from two standpoints. The first of which is sort of the moment in time when everything is frozen. I want you to think of our related rates diagrams as having the present situation, like a moment in time that's frozen, and this is exactly what's going on at that particular moment. So what we need to do is we typically need to either find quantities that represent measurements, or we need to find rates. Now in this case we're finding a rate of change right here, and I know that this plane is 6 miles off the ground and it's got a 10-mile distance directly to the radar tracking station. And if we did Pythagorean theorem and came up with how long the p distance is, you'd come up with 8. Okay? All right, now once again, this is where things get a little strange, but this is a constant. So let's see what I can come up with for my equation. P is going to be changing throughout the course of this problem, and S is also going to be changing throughout the course of this problem. So when I go to construct my equation, I can say 6 squared, because that's a constant, plus P squared is equal to S squared. All right, now I need to get these dP over dt to turn up, so that means I need to take a derivative. All right, so I'm going to come up here to kind of like right below my diagram, and I'm going to go ahead and do the derivative. So the 36 drops out, and it's going to be 2p dp dt is equal to 2s ds dt. All right, well, now we can put in what we know. Okay, so for example, we know that the p is 8, and dp over dt is what we're trying to find. And we know that the s is 10. We also know this is negative 400. So a little bit of algebra later will lead us to some information. And this is going to be negative 8,000. And if I divide that by 16, dp over dt is going to be negative 500. And this is going to be in feet, or miles an hour, rather. Okay. Now that we know that, by the way, it did say speed, so we do need to take the absolute value of this, just because speed is always an absolute value of velocity. So 500 miles per hour seems to be the answer to the question. All right, one more. Now we've got a police cruiser who's approaching at a right angle intersection from the north, and is chasing a speeding car that has turned the corner and is now moving straight east. Okay, so from the north, this police cruiser is coming this way, and going this way is the pursuit car. Okay, so we've got one car moving this way and one car moving that way. And once again, it looks like we could probably come up with a Pythagorean theorem equation. Okay, so let's read through and see what it says. It says when the police cruiser is 6/10 of a mile north of the intersection, and the car that it's chasing is 0.8 of a mile to the east, police determined that the distance between them and this car is increasing at 20 miles per hour. All right, well, I'm going to call this distance c, because it looks like we got a right triangle once again. But we know that dc over dt is going to be 20. We know this because, and it's positive 20, because that rate is increasing. Okay, now we know that the cruiser is moving at 60 miles per hour. Okay, so I'm going to call that dA over dt, and I'm going to mark it as negative 60. Now, why did I choose negative 60? I did that because as the police cruiser is getting closer and closer to this intersection, this 0.6 miles is decreasing quite a bit. So our job is going to be to find the speed of the pursuit car which is dB over dt, and that's the thing that we really need to know. But lucky for us, we can pretty well equate these things. By the way, another 6, 8, 10 right triangle here, so this c distance, this is 1.0 miles at this particular moment where we've got our snapshot. So if we've got all of our measurements and 2 of our 3 rates, then we can solve for the third rate pretty easily. So let's go ahead and do a squared plus b squared equals c squared. And again, I'm going with variables because as the cop car moves towards the intersection and the pursuit car moves away, this is also changing. So we've got a 0.6 that's changing, a 0.8 that's changing, and a 1.0 that are all changing. So as long as it's a value that changes, then we can come up with a variable in our equation. All right, so differentiate 2a times dA over dt plus 2b times dB over dt, or not 2b, haha, and 2c times dc over dt. And now I can start putting, I think dividing by 2 is probably appropriate here, so I'm just going to kind of take a red pen and cross out these 2's because I really don't need them in my problem if I can divide them all out. Let's just make this a little easier. Okay, so our A is 0.6 at this instant, and then our dA dt is negative 60. Our B is 0.8, and I want to know what dB over dt is, so that's going to help. That'll be our variable that I need to solve for. And then our C is 1.0, and then I'm going to multiply that by 20, because that's the rate of dC over dt. Okay, so this is 20, and if I did, let's see, if I did 6/10 of negative 60, I think I'm going to get negative 36. And now the math drops pretty quickly. So I'm going to take 56 and divide it by 0.8, and I end up with a rate of speed of 70 mph for this particular vehicle that I am pursuing. So it looks like the cruiser is going to have to step it up a little bit if it wants to catch the pursuit car. Okay, folks, that is our look at some related rates problems, and we will pick this up again soon. Be well.